Hello everyone, welcome back to Foolish Engineer. Today we are selecting a BMS IC for an e-bike battery management system the way we actually do it in the lab, from actual requirements to IC selection. Let's assume a battery is a 48-volt lithium ion pack with 14 cells in series, and our mission is simple, is to choose the right BMS IC that handles cell voltages, current sensing, MOSFET control, balancing, protection, and a clean path to firmware. So, let's start. One of the key reasons I started this YouTube channel is to bridge the gap between the outdated Indian education system and actual skills needed in the industry. Well, if you're a student, you can use and learn an industry leading EDS software, Altium, for free by using its student lab program, which narrows down this gap. You just need to use your university email to enroll, and you get a full student license, a full PCB design course, and a certificate recognized by top Indian core electronics industries. Altium isn't just one PCB design software, but it is a whole platform of capabilities for electronics design. I've personally used Altium since the start of my electronics journey, and I honestly recommend it. It's a fantastic way to enhance your skills and increase your chance of landing a job in a core electronics company. So don't miss this golden opportunity. We'll start with the job that BMS has to do in this e-bike. We are designing a 14 series lithium ion pack, which means managing about 36 volts when discharged and around 58 volts when fully charged. Our BMS has to measure each cell accurately, keep current under control in both directions, because acceleration and regenerative braking or charging are both real. So, we have to protect the pack from overvoltage, undervoltage, short circuit, and overcurrent events, and keep an eye on the temperature with a couple of thermistors. It also needs to switch charge and discharge MOSFETs cleanly and talk to the host microcontroller over a simple digital bus. That's the basic requirement. It should be safe, accurate, responsive, and easy to integrate. Right now, a main job is to select a BMS IC or analog front end for such BMS. The requirement for that is pretty universal. First and most important is, does our BMS IC support a cell count comfortably without a daisy chain? That means, how many ICs do we need to monitor the battery pack? Second is precise voltage monitoring for all 14 cells, because even few millivolt drift between cells can ruin balancing. Third, we need bidirectional current sensing, because during acceleration we pull the current out and during charging it flows back in. So our AFE should measure both directions cleanly and fast. The BMS must open or close the charge discharge paths in microseconds. If the AFE can drive the high side MOSFETs directly, that's the big plus. The BMS IC should be able to do cell balancing to keep everything equal during charging. And it should have all the protection logics like over voltage, under voltage, short circuit, over current, or over temperature. And the best one do this in hardware, so the system reacts faster even if the firmware freezes. We should also check how many thermistor inputs do we get, and can we expand if we need to monitor cells and MOSFETs separately. The IC should be able to talk to the host microcontroller either through I2C or SPI or any simple communication protocol. And finally, the underrated one, how fast we can get from unboxing the eval board to making a quick prototype out of it, because time to production is the real engineering problem. If you have seen our earlier videos on cutoff FETs and on current sensing, you already know we are very picky about three things: gate drive, shunt measurement path, and how quickly protection trips in hardware. These three define whether our design is elegant or very bad. Now, let's talk about the selection logic. With that in mind, let me walk you through the AFE that we are going to choose for now, the BQ76972 from Texas Instruments. And thank you to Texas Instruments for sponsoring this video. It covers 3 to 16 series range of cells, so 14 series cells are right in its comfort zone. It has a high side charge pump based N-channel MOSFET driver to control charge and discharge MOSFETs directly, which saves a lot of component count and effort. It comes with a high accuracy voltage monitoring system, a fully configuration protection subsystem, and support for both autonomous and host controlled cell balancing. Now, let's talk about cell balancing for a moment, because this is something that separates good AFE from the great ones. Balancing is how we keep every cell in the pack at the same voltage. Even small mismatch between cells can lead to capacity loss over time. This IC lets us control which cells to bleed, how long to bleed them, and even run balancing in the background mode. It's smart enough to handle balancing safely with built-in timing and voltage limits, so we don't have to worry about it. Then comes current management and Coulomb counting, which is the heart of the accurate battery gauging. The AFE has an internal differential current sense amplifier which is connected directly to a shunt resistor. It also performs Coulomb counting. Now, if you're new to that term, Coulomb counting is simply integrating current over time. In other words, it measures how much charge flows in or out of the battery. If the voltage tells us how the battery's health is, the Coulomb counting tells us how full battery is. The chip also features one-time programmable memory, so there is no need to send initialization commands or depend on external memory at startup. It just boots up. And since we are building a compact e-bike BMS, the AFE also has two programmable LDOs to power a local circuitry, maybe our MCU, sensors, or communication interface without adding an external voltage regulator. On the digital side, it offers I2C, SPI, and even HDQ one wire as communication options. In other words, the chip is designed to drop into exactly the same pack we are building today. And let us focus on the system behavior. Now, the important question is why to choose this BMS IC only? There might be some other AFEs out there also, and we should definitely look into those. Let's compare this IC with NXP's MC33771C. We'll start with number of cells. The NXP AFE handles about 7 to 14 cells. So both technically fit the pack, but the TI device gives us more flexibility if we ever scale the design up or down. For example, instead of designing the pack with NCS cell chemistry, we decide to use LFP cell chemistry, which has a cell voltage of 2.5 volts to 3.6 volts. So here we might need 15 LFP cells in series to design a 48-volt battery pack. So scaling with TI-IC is easier. The BQ76972 has built-in high-side NFET drivers for both charge and discharge paths, plus a secondary fuse drive output. That means our BOM is smaller and our protection logic is fully inside one chip. The NXP-AFE, on the other hand, is monitor only with no built-in drivers. We'll need extra gate drivers to actually disconnect the pack. That's some extra work. TI gives us I2C, SPI, or even HDQ one wire. We can drop it straight into small microcontroller without isolation when we are working on a single 48-volt module. The other AFE leans entirely on SPI or an isolated TEPL interface, which is great for large multi-stack system, but a overkill when all we want is one compact battery pack. Inside BQ76972, each cell channel includes an internal bypass FET with about 28 ohms of resistance, which takes care of 50 to 100 milliamperes of balancing current path per cell. The other AFE can drive much higher balancing current, but for a smaller pack, this would be sufficient. The TIIC accepts up to 9 external NTCs plus an internal temperature sensor, so we can track our cells, MOSFETs, and even ambient conditions. The other AFE supports around 7 configurable GPIOs or NTC inputs. In normal operation, the TIIC draws roughly around 286 microampere mode, 24 to 41 microampere, and in deep sleep around 9 to 10 microampere, with a full shutdown current close to 1 microampere. That's a very low leakage current, perfect for light electric vehicles. Plus, it keeps ADC measurements going periodically, and comparator predictions are running at full speed, monitoring under voltage, over voltage, etc. This is where the choice becomes obvious for small teams and solo builders. Honestly, this is the best part for the development. With the BQ76972, we can connect the evaluation module directly to our PC, open Battery Management Studio, which is BQ Studio, especially for TI devices, and we can read cell voltages and current in minutes. As an ecosystem, TI provides both hardware and software environments for easy development. The hardware through evaluation modules and also reference designs based on the device. And for software, we get the BQ Studio. We can change the protection thresholds, enable balancing, inject simulated faults, and log everything to a file without writing a single line of firmware, where we are ready to move it to our actual hardware. We can export the configuration and drop it into our MCU code. Even if the exact device name isn't listed, that saves days of coding and PCB design. It means we are validating device choices while the actual hardware is still in process. For this kind of 48-volt BMS, the white BMS IC is one with reliable, configurable, gives us real current measurement path, drives our high-side MOSFETs directly, balances cells, watches temperatures, and lets us configure and log everything on day one. That's why I'm choosing BQ76972. It meets the electrical requirements, it integrates the places we don't want to rebuild, and maybe most importantly, it comes with a development experience that lets us focus on the actual product, not on babysitting the IC. I hope you understood how to select the right BMS IC for the design. Check the Texas Instrument website to explore more on this. And if you haven't seen the earlier videos on cutoff FETs and current sensing, watch those next. They pair perfectly with what we have built today. If you found this video helpful, give it a thumbs up, subscribe to my channel, and stay tuned for more exciting content.